Hello everybody, it's Mrs. Pound and I'm back with the second video for Chapter 14 on solutions from BJU Chemistry's 5th edition. So the second video is a continuation of the first section on the dissolving process. Our objectives today are to explain how varying conditions will affect the rate of dissolving, solve solubility problems using a solubility curve, and apply Henry's law to the behavior of soda pop. So factors that affect the rate of solution. So how fast something will dissolve. The first is the solubility of a particular solute. The more soluble it is, so the more that will dissolve in a certain amount of liquid, the faster it will dissolve. Also, the number of collisions between the solvent and solute particles. So how quickly they're bumping into each other so that they will dissolve. Stirring. Now, stirring acts to increase those numbers of collisions by moving the liquid around. Temperature. Again, temperature increases those collisions as well because as temperature goes up, the particles are moving faster. And exposed surface area of solute particles. The more surface area there is, the more particles there are to bump into each other. Now let's take a look at solubility curves. You will find a solubility curve in your reference tables. And then reference table G, at the top, it says solubility curves at standard pressure. So first thing we want to notice that for solids, solubility increases with temperature because those collisions are increasing. And so anytime you see a curve going up, all of these positive slopes on the graph, those are solids. So some examples, and most of them are solids on here, would be sodium chloride. Even though it's not going up very much, it is going up a little bit. Potassium iodide, very steep right here, and potassium chloride also going up. And others too, potassium nitrate, sodium nitrate, all kinds of solids on this chart. Now, gases, on the other hand, their solubility decreases with temperature. So anytime we see a line with a negative slope, that it is decreasing, we have a gas. And those gases would be hydrogen chloride here, ammonia, NH3, and sulfur dioxide right here going down. So these are all gases. And the reason for that is that as gases get heated up and more excited, they want to change state. They want to, well, they're already a gas. They want to escape, though, from that liquid. So a question you might see based on these solubility curves is, what is the solubility of NaNO3 in 100 milliliters of water at 20 degrees Celsius? So first of all, if we look at this, it says solubility grams of solvent per 100 grams of water. Remember, since the density of water is 1 gram per milliliter, 100 grams of water is also 100 milliliters of water. So grams and milliliter is interchangeable for water here. And our temperature scale is down here. So what we would do is we would go down to the 20 degrees Celsius down here. Just look for my arrow here, my pointer. We would go up until we hit the sodium nitrate line. So we're going up, oh, it's right here. This curve right here at 20 degrees. Then what we do is we go over to our y-axis, and it's just under 90. So I would say that that's about 88. So its solubility is 88 grams in 100 milliliters of water. Another thing we can ask is, at what temperature is the solubility of sulfur dioxide 15 grams in 100 milliliters of water? So we do this the other way. We find 15 over here, which is like halfway here. We go until we hit the curve, which I know it's hard to see here, but it's actually a little bit beyond the 10. And then we go see where that is. We go down. And I said that that was about 12 degrees Celsius, give or take a degree or two. Another question is, which compound is most soluble at 20 degrees Celsius? So I would go to my 20 degrees Celsius here again, and I would go up. Now I'm going to go to the topmost line because that will have the most dissolved. And so it's this line here for potassium iodide. Another question we might ask is, which compound is least soluble at 80 degrees Celsius? So if we go to 80 here, 80 degrees Celsius, and we go up, it would be the first line we hit because that will have the least amount dissolved in 100 milliliters of water. And so that line is the line for sulfur dioxide. Now, the last thing I want to talk about is Henry's law. This is the solubility of a gas is directly proportional to the partial pressure of the gas above the solution. So, gases, when dissolved in a liquid, are affected by the pressure. The higher the pressure, the more gas will dissolve in the liquid. The lower the pressure, the less will dissolve. So this describes the relationship of carbon dioxide dissolved in canned beverages, like the pop in the background. An unopened can of soda pop represents a liquid gas solution at equilibrium. What that means is when it has the cap on here, that you have some gas coming out, some gas going in. Okay, but it is at equilibrium and it's not in motion. However, you open that can, it releases the pressure, the solubility of the gas decreases because the pressure goes down, so the solubility goes down, and the gas escapes. That's what causes all of that bubbling. And we call that effervescence, and this is the escape of a gas from a liquid gas solution. So our objectives for this video were to explain how varying conditions will affect the rate of dissolving, solve solubility problems using a solubility curve, and apply Henry's law to the behavior of soda pop. So I will be back with another video for this chapter.